produces magnetostatics via the Biot-Savart law. In fact, if you consult the books on electricity and magnetism, most of the book starts the magnetism, the chapter on magnetism by the Ampere's first law. However, here I have considered some alternative approach. We first want to address how the magnetic fields are produced, and then we shall go on to the force on the current element when placed in the magnetic field. Electrostatics, earlier we have studied electrostatics. Electrostatics is the subject that deals with the electrical charges at rest. When the charges are in motion, electric current is produced. If the magnitude of the current does not depend on time, then we call it as a steady current, and magnetostatics arises due to the steady current. From prehistoric prehistoric time, it was known that the ferrosulfuric oxide, which was obtained in Magnesia, present day in Turkey, have the directional property and attracting property, attraction or repulsive property. The material was called the magnet. Afterwards, Ørsted performed a series of experiments to show that when a current carrying a magnetic needle is placed in the vicinity of a current carrying conductor, the magnetic needle gets deflected. And it was concluded by Ørsted that a current carrying conductor produces a magnetic field in its neighborhood, and the direction of the magnetic field so produced could either be given by Ampere's Untitled law or the right hand rule. Here we consider a current carrying conductor in the form of a wire. A conductor in the form of a wire, the C is the locus of the wire, and a steady current I is flowing through the conductor. I is steady, means it doesn't change with time. Let us consider a current element, a length element. So this is a portion of the conductor which has a coordinate r prime, the source coordinate which we are using all along. And if we are interested in finding out the field at point P having the position vector r with respect to some suitably chosen origin O, then this is the r, the relative position of the field point with respect to source point, and it is given by r minus r prime, and this is the change in length, and this is the r prime. So ideal prime is called the current, dr prime is called the current element. It is a vector quantity. If we want to find out magnetic induction at P due to this, it is found that magnetic induction B, it is equal to mu 0 upon 4 pi I dr prime cross r by r cube. It is actually proportional to the inverse square of the distance, proportional to I, proportional to dr, and proportional to the angle sine theta between dr prime and r. If we want to find out the total field produced by at P due to the entire conductor, then B is given by integration over B over the conductor, and this is mu 0 I upon 4 pi dr prime cross r by r cube integrated over the conductor. So everything related to source is denoted by a prime, so we put a prime over the curve traced out by the conductor. This is the law of, this is the Biot-Savart law, for a filamentary conductor or one-dimensional conductor. Sometimes current flows across a surface. Consider a surface like this, which carries a current I. This surface may be looked upon as made up of a large number of wires placed side by side, just like a mat. Then each one of these can be considered as a wire. So all these wires all together carries a current I. So the current per unit lateral area, so Js is called a current per unit lateral length. This is called the surface current density. Note that surface current density is current per unit length. Surface current density, it is the current per unit length. It is a vector quantity and it is in the direction of the current flow. So if we have the surface, the two-dimensional conductor to be like this, then Js is along this, it is along this, so it will be along this, it will have a changing direction. So we call the current density as a vector, and accordingly this law becomes the Biot-Savart law for a 2D conductor. So to say this is the Biot-Savart law for a 1D conductor, for 2D conductor Biot-Savart law becomes for an current element mu 0 ds prime, and total field is given by integrated over the surface. So S prime is the surface of the conductor. And finally, for 3D conductor, one defines the volume density of current. Let us consider current to be flowing through a thick wire. So the total current is flowing I across this surface area alpha. Then one defines the current per unit area. So volume density of current is defined as J. So J is defined as current per unit area. So if this cross-sectional area is alpha, then the volume density of current is given by I by alpha. Again, this is a vector, and the vector has the direction in the direction of I, and it is a variable. It is a variable, means it may change from point to point. So for 3D conductor, Biot-Savart law becomes mu 0 upon 4 pi and the total field at a point is obtained by integrating mu 0 upon 4 pi where V prime is the volume over which the current is distributed. If you want to find out total current in this case, total current is simply J dot ds if current flows through a closed surface. So these are the three alternative forms of Biot-Savart law. This is for applicable for filamentary conductor, that is where it is two-dimensional conductor, it is the three-dimensional conductor. To find out the field due to a current carrying conductor, there are two laws of in magnetostatics. One is the Biot-Savart law that we have already stated. It is basically an inverse square law, as is apparent from each of the expression, that it varies as 1 by r square. And another law is called the Ampere-Circuital law, which also describes the magnetic field produced by a current carrying conductor. So if Biot-Savart law be a correct law of magnetostatics, then one can also derive Ampere-Circuital law starting from Biot-Savart law. And there is another basic law of magnetostatics, is the Gauss's theorem of magnetostatics, which states that magnetic monopole is not obtainable in nature. That is, the differential form of Gauss's law of magnetostatics is this, and the Ampere-Circuital law has a differential form is this. So we must be able to find out these laws from this theory. So to start how to prove this law, we should start from the Gauss's or Biot-Savart law in three-dimensional case, and we will land up to there. So first we start with the magnetic field produced by a current distribution. Magnetic field which is produced by a current distribution. This is the field at R. This is equal to volume. dV prime. This is the three-dimensional case. If you have in a particular case the conductor is in a form of a surface, then we can write this dV prime is replaced by ds prime for 2D conductor, and for 1D conductor it is I dr prime. From this relation, it is found that it would be better to put the vector over I, because this is in the direction of I, this is also direction of I. But here, historically, current was treated as a scalar, so the current vector sign is not assigned on I, rather we follow the conventional norms. So this describes how one can go from three-dimensional case to one-dimensional case. Now first let me write it as gradient of 1 by r is minus which takes into account r by r cube, and the minus sign has been adjusted here. This we write as mu 0 upon 4 pi we have changed the order, and which adjusts as the minus sign. Curl of this has two terms. One is this, another term as actually curl of phi times A is equal to grad phi to curl A plus phi times curl of A. So we have this term, so this is equal to this minus this. Now you see that this differentiation is over the source coordinate, field coordinate. This is the field point operator, and this is a function of source coordinate, so it is 0. So we can write it as mu 0 upon 4 pi. This differentiation is with respect to field coordinate and integration is with respect to source coordinate, which are independent of each other and can be interchanged. So the resulting quantity is curl of mu 0 upon 4 pi this quantity upon integration is a vector which is a function of r only, and it is called A of r, called the vector potential. So the result is curl of A of r, where this is known as the vector potential. This is defined in 3 dimension. In 1 dimension, 2 dimension, it is mu 0 upon 4 pi and in 1 dimensional case it is mu 0 I upon 4 pi This is the definition of vector. These are known as magnetic vector potential. As we shall see later, that since the divergence of B is 0, the magnetic field or magnetostatic field can be represented in terms of a vector potential. Remember the decomposition theorem of a vector field. So, since divergence B is 0, magnetic field can solely be described by the vector potential. On the other hand, the electrostatic field has 0 curl, so electrostatic field is completely described by the scalar potential. So this is the vector potential. So if we want to find out the divergence of B is equal to divergence of curl of A which is 0. Gauss's theorem of magnetostatics. This signifies monopole magnetic this is the physical significance. Now, with this expression, we shall go to prove the curl expression. So, we have this is curl of A of R with with A of R is equal to mu 0 upon 4 pi So our aim is to find out the curl of curl of V, which is the differential form of Ampere's Untitled Law. So if we want to calculate curl of B, this is, I am omitting the argument R, this is curl of curl A. Using the vector identity, this is divergence Let me first consider this term. Divergence of A at R, this is equal to divergence of A. You remember the definition of A, mu 0 upon 4 pi mu 0 upon 4 pi taken out, and we take this within the integration sign. So it will have two terms. These two terms. We have used that divergence of phi times A is equal to phi times divergence A plus grad phi dot A. This is this term. Oh, sorry, this is this term and this is the. You see that this differentiation is over the field coordinate, and this is the source coordinate function, so this part is 0. So we have mu 0 upon 4 pi we change the differentiation from field point to the source point. So the geometry that we are using is this. This is a point R prime, which and a volume element is there, dv prime, and we are interested in finding out the field at R. So this differentiation means we were differentiating with respect to this. If we shift it from here to there for a fixed separation, the minus sign will come. So to say, this is mu 0 upon 4 pi dv prime. Just we have shifted the differentiation from here to there. So we write it and is as it will have two terms. One is this, and the extra term that has been added is subtracted out. So this will have two terms. One is this term and other one is this. Now we do the equation of continuity. Come to equation of continuity. In a conserved quantity, if we have a quantity which is conserved, then it can be expressed in terms of a differential equation called the equation of continuity. Now we consider a volume V bounded by a closed surface S, and the charge density within it is given by rho, and the volume density, current density is given by J. So the current that is flowing out across this surface is going, the flux of current is J dot ds, where S is the surface. See, this gives you the amount of current that is flowing out through the entire surface in this represents the total amount of charge that is flowing out across the closed surface per unit time. That is the amount of current flowing out. If the charges are constant, so no charges is created within this volume, then it must be equal to the rate of loss of current. So rate of loss of current is minus ddt of rho dV. So if we take this within the integration sign, it will be minus del rho del T dV, del rho del T dV, because this, once the volume space integration is carried over a definite volume, it is no more a function of space, only time, function of time. That's why we use total derivative. When this differentiation is taken within the integration sign, the integrand is a function of space as well as of time. That's why we have used the partial, not time derivatives. And if we convert it into the corresponding volume integration using divergence theorem, this is divergence d dv. So it represents that divergence J plus del rho del T is equal to 0. It is the equation of continuity, which signifies the conservation of charge. If we are dealing with a steady state affair, then the rho is not a function of time. So in the steady state, this divergence J is 0. So this part is 0 in steady state. So we come to now the volume, the charges is distributed only within this volume V. This volume V. If we add a larger volume over V and call it tau, then this part, the added part, does not contribute anything to the field, because there is no charge or no current within this extra added part. If we then convert it into the corresponding larger volume, we have this is the larger volume tau prime, and this can be converted into the surface integration, where sigma is the closed surface bounding tau, and this is This quantity, the integrand specifies only on the surface sigma, and since there is no current, this is 0. In other words, if we consider the charges to be confined within, the current is confined within this region, then there should not have any normal component of current on the surface S bounding the volume B. So in that case, the current density can at most have tangential component on the surface, and this is the normal to the surface, so this quantity is 0. Either way, this is 0, so we conclude this part is 0, so it doesn't contribute, and this is the result. Now come to the second part. Similar calculation we have also performed in the connection of decomposition theorem. So this is equal to simply minus AR. Now consider this quantity. This is equal to mu 0 upon 4 pi minus mu 0 upon 4 pi we interchange the order of differentiation and integration, and we find that this is a function of prime coordinate, so differentiation does not operate on it, and it operates at 1 by r dv prime, and this result is minus 4 pi delta of r, delta function, that is equal to minus 4 pi delta of r minus r prime. So if we write this minus sign is adjusted, the result is plus, and the 4 pi in the numerator is cancelled with the 4 pi in the denominator, so the result is plus j of r prime delta of r minus r prime integrated over v prime. So the result is mu 0 j of r, not of r prime. We use the property of delta function, that f of x prime delta of x minus x prime dx prime is equal to f of x. So which satisfies which establishes the Ampere's circuital law. Yes, yeah. So if today what we do is that we have started that the magnetic field can be, the current carrying conductor produces a magnetic field in its neighborhood, which can be calculated using Biot-Savart law, and we have then proved establishes the 3 alternative forms of Biot-Savart law as applicable to the surface volume distribution of surface current and linear current and volume currents. Then there are other laws of magnetostatics, namely the Biot-Savart, like Ampere's circuital law and Gauss's law. We have proved these 2 laws starting from Biot-Savart law. In the next class, we shall show few simple applications of Biot-Savart law.